Rafael Benguria here, all the way from Chile, and he'll tell us about estimates on the L2 norm of the positive solution of this parameter family of nonlinear PDEs of the Thomas family bicycle type.
Thank you very much for the opportunity to give this seminar and for the invitation to be part of the semester. I'm sorry about the long title. I mean, this is sort of like inspired by physics, and in physics the title will be much shorter, as I am going to tell you. And before I go to the PowerPoint presentation, I would like to tell you what I'm going to tell you, because otherwise we're going to get lost. So what I want to discuss today is this nonlinear PDE. This is in R3, and psi is the unknown, and I would like to study the fundamental solutions of the positive solution psi. So this is a nonlinear equation, and in principle, to be part of the semester, you can consider this as to be a spectral problem. And there is an eigenvalue here, which in physics is called the chemical potential. And so you are interested in trying to solve this equation, at least to find the fundamental solution. And the 5 here is the Coulomb potential. So 5 of x is the Coulomb potential produced by k positive charges, like Ci bigger than 0. And Ri is the position of the charges. They are fixed, and they belong to R3. So this is the potential created by a set of nuclei, and psi, as I'm going to tell you later, represents on the square. The psi square represents the density of the electrons. So that would be the physical meaning. But you're not interested in the physics. This is the question I'm going to discuss. And there are two parameters here: gamma, which is a coupling constant, which is non-negative, and an exponent p, which is bigger or equal to 1. And what I would like to understand, to estimate, is the L2 norm of the solution, of the positive solution, when the chemical potential is 0 for the 0 eigenvalue here. That's the goal. And so this is the main quantity we're interested in. And we would like to see how this changes when you change the parameters, gamma and p. Okay, so keep in mind that that's the equation I would like to study. All right. And before I go to the results, the results can be all summarized in this picture. So in this picture, this a two-dimensional. I mean, there are two parameters here. So here in the horizontal axis, I have the coupling constant gamma. In the vertical axis, I have the exponent p. And there are two features here that are important. I mean, the physical situation corresponds to having p equal 5/3, as I'm going to describe later. So if you are interested in the physical situation, it's just the first line. And a very easy case is the p equal 3/2 case, which corresponds to a scale invariance in the problem. So when you have a sort of like a scale invariance in the problem, the coupling constant plays a fundamental role. So in the 3/2 case, there is a critical value of the coupling constant here, that for which you have different behavior if you are above the critical coupling constant or if you are below the critical coupling constant. And for when you are above the critical constant, this quantity that I have here, Q, which is n minus c, c is the total charge of the nuclei, so the sum of all the little charges of each of the individual nucleus. N is the total number of electrons, which is represented by the L2 norm of psi square. And
Q. Why is it an integer?
What?
Why is this an integer? The number of electrons is an integer?
No. No, sorry. In physics, n is an integer, But here in math, I mean, n can be anything, right? I call it n because I'm a physicist and I would like to have it, but n is not an integer necessarily. So n is the true norm of psi, okay? And q is n minus c, the difference between the total charge of the electrons and the total charge of the nucleus. And we call that the excess charge. And when P is equal to 3/2, there is this critical coupling constant. Above that, Q is equal to 0. And below the critical constant, Q is bigger, strictly bigger than 0 in that situation. And from the physical point of view, I mean, at least if you are in the P equal 5/3 case, Q represents what we call the excess charge, the difference between the charge of the electrons and the charge of the nucleus. And this is a very important problem in physics, which is not totally solved, right? I mean, if you see matter here in this room, the matter is essentially neutral. I mean, if it weren't neutral, it would be a disaster, right? So suppose you have 1% more electrons, more electrons in this leg and 1% more electrons in the other leg. The force will be so big that nothing will hold. So it's fundamental. It's fundamental to have what we call the neutrality of matter. I mean, at most you have one or two electrons, one electron per atom, and that hasn't been proven still today. I mean, this year is the 100th anniversary of the Schrödinger equation, and one of the big open problems is to prove the neutrality of matter, right? And this what I'm going to talk about is not the solution to that problem, but is part of the whole scheme. So when P is equal to 5/3, in that case, and if gamma is sufficiently big, a long time ago I proved with Elliott-Lib that Q is less than 1, which is what we would like to prove in general, not for this particular. This is just a model. I mean, it's not the real Schrödinger equation, as I'm going to describe later. So for when the exponent there is the physical exponent, 5/3, and gamma is sufficiently big, Q is less than 1. And so in principle, we would restrict just to the first line, but it's nice to have, from the mathematical point of view, it's nice to study the whole thing in the parameter space gamma and P. So that's the goal of my talk. And one can prove in general for any P bigger than for any P bigger than 1 can prove that Q is less or equal to C. So that's very easy when it's not, once you realize the proof, it's very easy. So it's very easy to prove that N is less than 2C, which is not what you want, right? I mean, the real, what you would really like to prove is that Q is less than C plus 1, which we do in this particular model. Okay, so that's what I'm going to discuss. So the main goal is to concentrate our attention in that problem when the eigenvalue is 0, when the chemical potential is 0, and the goal is to estimate the L2 norm of psi.
So why is it important to show that Q is less than 1?
Huh?
Why is it important to show that Q is less than 1 from physics point of view?
I'm going to tell you how to prove that.
No, but why is it important? You said it's very important.
I mean, there is, as I said,
so you said it moves 1 electron
in excess.
Why not 2? I'm asking because I don't understand this.
Well,
you think the answer is 1?
I mean, nobody has ever seen a negative ion with more than 1 electron in the lab or they typically nowadays, instead of doing the lab thing, they investigate the atmosphere of the atmosphere of planets, and they can by looking at the atmosphere, they can see what sort of elements there are, and nobody has ever seen something with some atom or molecule with more than one electron. And this is not the real physics, because the real physics is described by the Schrödinger equation and not by these models. But so that's a known experimental fact, and there's a conjecture to prove that mathematically using the Schrödinger equation, and nobody has ever proven that. So that's an open problem.
Another question. For this model problem, can you explain the origin of this nonlinear term and why pi 5/3 is the physical one?
Yeah, I'm going to do that now.
Okay.
So I'm going to do that now. But in order not to get lost in the middle of the talk, I wanted to know what the problem is. From the mathematical point of view, what I would like to study is this. And as a function, and in terms of the two parameters, gamma and p. And gamma, I mean, from the physical point of view, there is a special value of gamma. And from the physical point of view, the only exponent that matters is p equal to 5/3. Yeah. But that's what I would like to discuss. All right. So this is a joint work with Heinz Siedentop from the Ludwig Maximilian University in Germany, in Munich, and that appeared in the Journal of Mathematical Physics. So the summary. What I. That's fine.
Good. I think it's okay.
So this equation is the Euler equation. This is in the p equal 5/3 case. This is the Euler equation corresponding to. Sorry. This is the Euler equation corresponding to this functional here. Rho is the electronic density, and it's a positive function. And here you have gradient of square root of rho square plus these three terms there. And this is related to what you were asking. So from the physical point of view, in principle, one should study the Schrödinger equation. And this is an approximation to the expectation value of the Schrödinger equation in a Hilbert state. In a function. So you have the Schrödinger equation for an n particle model, and you take a function psi, which is in the fermionic state. So it belongs to the antisymmetric tensor product of tensor products of copies of L2 of R3. So and rho is the single particle density, which you can. If you have the state in the Hilbert space, you integral psi square over all the electronic coordinates except one, and it doesn't matter which one because the function is antisymmetric, and you normalize by you put an n, and the integral of rho is going to be the number of electrons. And all these terms here, especially these ones, they represent an approximation to the expectation value of the real n particle Hamiltonian. And so, when you do the expectation value, there are three terms, and the only one that exactly represents the expectation value is the second one. The attraction of the electron by the nuclei. So if you have a function psi in the Hilbert space, and you define the single particle density to be like the integral of psi squared times integrated over all the coordinates, then the expectation value of the attraction of the nuclei of the electron by the nuclei is exactly that. And the other two terms this represents the kinetic energy of the electrons, and this represents the repulsion of the electrons. And they are not exact at all. The only exact term in terms of rho is the third one there. But if you have enough feeling for electricity and magnetism when you have a cloud of charge given by this density rho. This d rho, which is this quantity here, is precisely what you would like to say is a Coulomb interaction between the cloud with itself. So it's not the right term from the physical point of view, but it's more or less natural. And this represents the kinetic energy. And for the kinetic energy, what you do is the formal approximation. Suppose you have an ideal gas of electrons in a box, and you and suppose they don't interact, so that's so that's why it's ideal. And you put one electron. I mean, and you try to study the ground state of the system of electrons in the box, and you use the Pauli principle. So you say we're going to put one electron in the ground state, the second electron in the second state, and everything up to until you fill all the levels. And and you can and when you do that, you can prove. I mean, you can compute the energy of this system, and that's going to be proportional to the number of electrons divided by the volume to the 5/3. So that's related to the bias. So this exponent here, 5/3, comes from the fact that you are using the Pauli principle and filling all the levels up to the Fermi energy. And so that's that. If you neglect the first term here, which I'm going to tell you something about later, this is this variational principle that's a function of rho. Is what defines the Thomas Fermi energy. And the Thomas Fermi variational principle was introduced in 1927, a year after Schrödinger introduced his equation, because to solve the Schrödinger equation, except for the hydrogen atom, it's a very complicated business. And they say, and that's why Fermi and Thomas, they introduced what they call the statistical model of the atom. And so instead of using the Schrödinger equation, you just use this variational principle in terms of rho, which is relatively easy to study. In the Thomas Fermi case, you can prove easily that there are no negative ions. So there are positive ions or neutral atoms. And so and that's what it's going to be behind all what we do here. And so that was done by Thomas and Fermi in 2027, and later in 1935, von Weizsäcker introduced a correction to the kinetic energy, which is given by this quantity here. And in the Thomas Fermi and that's called the Thomas Fermi von Weizsäcker, the variational principle for the Thomas Fermi von Weizsäcker model, and then in that model the maximum charge is not. I mean, there are negative ions, but as I will tell you, the maximum charge is going to be 1. The most negative ion will have only 1 electron. So that variational principle defines what's called the TFW model. And the rigorous study from a mathematical point of view of the Thomas Fermi von Weizsäcker model, I did it a very long time ago, before you were born, when I did my PhD thesis. And then we published a paper about that thing with Chaim Bressis and NLDB in 1981. So you want to study to see all the properties of the TFW model. Most of the things are there. And
is it the rigorous study of the connection with Schrödinger, or the study of this? Is the connection with Schrödinger rigorous, or is the study?
The connection. I mean, that's a good question. The connection between the Thomas Fermi model and the real Schrödinger stuff was done in 1977 by Elliot Lieb and Barry Simon, and they study they had a very long paper in Advances in Math, and they study all the properties of the model. I mean, of the variation for the Thomas Fermi, only with these three terms, right? With p equals 5/3. So they study the mathematical properties of that, and also they study, more important, they study the connection between the expectation value of the Schrödinger equation and that in the limit of when the charges are very high. So they prove that when the C's go to infinity, and you study the quotient between the physical quantities in the Schrödinger equation and in the Thomas Fermi model, that goes to 1. And so that was done in 77, also a long time ago. And the Thomas Fermi von Weizsäcker model, the grading correction that I put there, we did with Chaim Bressis and Elliot Lieb in 1981. And so one is concerned with, I mean, from the point of view of the variational principle here, one is concerned with minimizing this energy in the proper space in the one intersection of Rp, and with this restriction integral of rho to be n. So from the point of view of not with the connection of the real Schrödinger equation, but from the point of view of the Thomas Fermi von Weizsäcker problem, the thing to study is this minimization problem.
And it's always on the full R3, not on some domain.
It is in the whole R3. Yeah, I mean here what holds the electrons together is the Coulomb potential of the atom. It's not the. So there is no. I mean, you can also study it in a box, but it doesn't. And also people study in for periodic potentials B. I mean, in sort of like in a crystal too. So there are lots of things there. And this is what and you study the Euler equation for the minimization problem. As I said before, you get that thing, which is this equation here. And as I said before, 5 is the Coulomb potential created by the nuclei minus the potential created by the electron. And here, so sorry, I forgot. This is just B, not 5. So the potential, the B is that, right? And 5, the Coulomb potential is the difference between the Coulomb potential of the nuclei minus the potential of the electron. Sorry, I should have said B there. And here, psi denotes the positive solution, and as I said before, n is the integral of psi squared. That's the number of electrons, and it's not an integer necessarily. And in the paper in 1981 with Chaim Bressis and Elliot Lieb, we proved that there is a critical value of n, which we call n critical, that depends only on P and B, such that if n is smaller than this critical value, the Euler equation has a unique solution, and if n is bigger than nc, the minimum is not attained and there is no solution. I mean, the electrons for n bigger, so nc is the maximum charge that the system can have, and if n exceeds, if the number of electrons is bigger than nc, the electrons prefer to go to infinity. And so nc is the maximum charge, and as I said, it's important to prove that nc is less than 1 for appropriate values of the constant. And we also proved that if the exponent p is bigger or equal to 4/3, then n critical is strictly it's bigger or equal to c, and when p is 5/3, which is the Thomas Fermi, which is the physical value of p, and in the atomic case, when there's only one nuclei, then we can prove that n critical is strictly bigger than c. And at that moment in 1981, there were lots of things that we haven't that were still open, and one of the things that we need to this is still open. I mean, when you have a molecule with more than one nuclei. Is it true that the uncritical is strictly bigger than C? That we don't know. And the key thing open in that paper is to find estimates on uncritical. And there is, I mean, when the number of nuclei is one, for the atomic case, it's extremely simple to prove that the critical is less than 2C. So I did that in 1981 for the atomic case, and then Elliott Lieb extended it to the molecular case, and the same result. And recently, in 2022, with a student of mine, with Trinidad Tubino, we lowered that thing from 2C to 1.5 to 11C. And also, we only did it for the atomic case. I don't know how to do the new result in the molecular case. Okay. And in 1985, with Elliott Lieb, I proved that the excess charge in the P equal 5/3 case, the difference between the number of electrons and the number of nuclei, and the charge of the nuclei, is bounded by this constant. K is the number of nuclei, A is a constant independent of gamma, P here is 5/3, and you have gamma over T in the denominator. So if gamma is big enough, surely you prove the conjecture, at least in this model, that n is less than C plus 1. So for gamma big enough, in the P equal 5/3 case, it is true that Q is less than 1. Which, okay. Yeah. So in the easiest, the simplest case that one can study in this equation is the scale invariant case, which corresponds to P equal to 3/2, which is the equation 1 in there. And again, 5 is the Coulomb potential created by the nuclei and the electrons, and B is the potential. And
do you call it scale invariant?
What?
Why do you call it scale invariant case? Phi is not scale
You sorry?
Why do you call it scale invariant? Phi, I mean, the equation looks like it's scale invariant, but phi itself depends on psi squared.
No, I mean, you can have a solution to this problem. I mean, there's a scale in this problem that disappears. I can show it to you later. But okay, I can discuss that later. So P equal 3/2 case, I mean, there's a scale that disappears from the problem. We can discuss later. And so in that case, the coupling constant plays a fundamental role. And what we managed to prove is the following. So if the coupling constant is big enough, and big enough is bigger than this critical value there, 4 square root of pi, then Q is exactly equal to 0. And if gamma is less than the critical constant, Q is bounded by this quantity there. And we don't have, I mean, when gamma is less than the critical constant, we don't have a good estimate for Q. I mean, it would be nice to prove that Q is linear at least linear in C. And now when P is between 3/2 and 2, we can prove the generalization, the result that I proved with Elliott Lieb in 1985. So we can prove when P is between 2/3 and with 3/2, which is the case that I was discussing before, and 2, one can prove that Q is the minimum between C and that quantity. So again, if gamma is big enough, Q is less or equal to 1. And in order to prove that, you use comparison theorems all the time. So the proof of this the proof that of these facts is more or less as follows. So when you are in the p equals c half case, the first thing we do is to prove this quantity. We can compare psi with the potential v, the potential of the nuclei. And you can prove that everywhere psi is less or equal than 1 over gamma times v. And for that, you just use comparison theorems. So this standard thing, I mean, the Coulomb potential is harmonic away from the nuclei. And now you can define, in order to prove that quantity there, you define f, the function f, to be the difference between these two guys. And you want to show that f bigger or equal to 0. So you study the set where the function psi and this function f is negative. And of course, since the potential blows up at the nuclei, all the nuclei are not in this region S. And on S, you just compute the Laplacian of phi, and you prove that it's negative. So the function f is superharmonic there. And in the boundary, of course, f is equal to 0. So if the function is superharmonic and in the boundary is 0, then the function is positive in S, and obviously S is empty. So that's the standard things we use all the time. And in order to prove that Q is Q is equal to 0 when gamma is bigger or equal than the critical constant, again you use comparison theorem. But now you define, instead of defining F to be the difference between these two things, you define G to be the Coulomb potential plus a constant B and minus B of psi. And A and B are going to be chosen later. And again, you define the set S as the set where the function G is positive. You compute the Laplacian, you prove that the function, the Laplacian is going to be negative, the function is going to be superharmonic, and then it's very easy to prove that the bounds. So in order to, there are two results above and below the critical constant, and for proving when gamma is bigger or equal to gamma c, you choose the constant a equal to 0, and you do the same sort of trick as before. I mean, sort of method as before, and you have the result. And when gamma is less than equal gamma c, you have to choose different these a and b. Okay, anyway, by using comparison theorems, you can prove this theorem that when gamma is bigger than gamma critical, the total charge Q is 0, and when gamma is less than gamma critical, Q is bigger than 0. Okay, the most difficult, I mean, the most difficult result is to prove the equivalent of that quantity when that Q is less than a constant like that. And the way to prove that, that's what we want to prove. When P is between C halves and 2, we have that Q is less than the minimum. These two quantities, and if gamma is big enough, Q is less than 1. And what is the rationale behind the proof? In the Thomas Fermi case, when you don't have the gradient is a perturbation, somehow a perturbation of the Thomas Fermi thing. In the Thomas Fermi thing, in the Thomas Fermi model, the maximum charge is always 0. There are no negative ions. Yeah, and that's easy to prove. And so if the Thomas Fermi is the von Weizsäcker correction, you consider that as a perturbation. You would like to sort of like try to use the fact that you are very near the Thomas Fermi thing, and try to use the fact that in Thomas Fermi there are no negative ions. So what we do is the following. So define that function p there, which is the square root of psi squared plus 5 squared. 5 is this guy, is the Coulomb potential created by, as I said before, by, the total Coulomb potential produced by the nuclei and the electrons. So you define p to be that square root, and you can prove using this equation and the definition of the potential 5. You can prove that the function p is subharmonic. It's subharmonic in the whole R3 except at the position of the nucleus. And so given that p is subharmonic, you can prove that RPR is a monotonically decreasing function of R. And in particular, we can prove, you can study the behavior of p for large values of q. So when R is mod x, at large distances, the function psi decays, and in fact it decays exponentially. So the only thing that matters near at infinity is the behavior of the square root of 5, of mod 5. And when R goes to infinity, the PR times R goes to Q. And you can evaluate RPR at 0, and the only psi near in the atomic case 5 goes like C over R. So you can at 0 RPR goes to C. So given the fact that given the fact that RPR is the monotonically decreasing function, you compare the value of that function at 0 and infinity. At 0 is C, and infinity is Q. So you have all that. So that's the starting thing. You can prove, and so that's a different proof of what I told you, that Q is less than C everywhere. And now, so you use the definition of P, and then by using comparison theorems and the equation for psi and the equation for phi, you can prove this point-wise estimate of psi in terms of phi. And the last thing you use is how can you use the fact that you are close to the Thomas Fermi situation. So if you write you can consider this equation in the case of 5, 0 equal to 0 as an equation of the form minus Laplacian phi plus a potential times phi. So that equation there is sort of like, if you consider this as a potential W, this is a Schrödinger equation with a 0 eigenvalue. And if there is a solution to this equation with 0 eigenvalue, then it turns out that for any b in H1, the expectation value of this thing is bigger or equal to 0. And now you use that thing in the following way. So this is true for any b. And so the thing is, in order to use the fact that you are close to Thomas Fermi, you use a little length. You use a function b that you choose as the E as the ground state of the Dirichlet Laplacian on a ball of radius r. So you have sort of like a little length to do that, and so you choose E to be the ground state of the Dirichlet Laplacian on a ball of radius L, and then you define and then you move this around. So B of x I is the translation of that thing there. So by doing that, you can essentially reduce this equation to the Thomas Fermi a Thomas Fermi equation of this form. So if you define psi twiddle to be the convolution of phi with this little length, and b is a constant, you can prove that psi twiddle and rho twiddle you also define in the same way. You can prove that psi twiddle and rho twiddle satisfies a Thomas Fermi equation. And you can sort of, it's Thomas Fermi not equation and Thomas Fermi inequality. And then you can study this inequality in order to get bounds on 5 twiddle and rho twiddle. And essentially, and later you can have bounds on 5 and rho. And once you have the bounds on psi and 5 and on rho and 5, you use the fact that the function that RP is you use the fact that Q is bounded from above by RPR. So this is Q less or equal than RPR is true for every point for every R, and you have bounds for psi and rho, and so you plug the bounds that you obtain for psi and rho everywhere, and then you can have a bound of Q that's independent of the charge C. And so at the so you can the typical bounds on psi are of this form. This is sort of like a localization error, and this is the Sommerfeld solution, the solution to the Thomas Fermi for large values of R. And then you plug these values of 5 and rho everywhere, and then you get that the Q is less than that constant over there. So that essentially proves what we wanted to, and so that's all I wanted to say. Thank you very much.
Okay. Questions, comments?
Very naive question. Do people study these questions in curved spaces?
Excuse me?
Are these questions studied in curved spaces as well?
I don't know. I mean, probably you can discuss this in a curved space, and probably, I mean, they're not. They have not been studied, yeah, because in principle the problem. I mean, that could be studied, right? To change the Laplacian by the Laplace-Beltrami operator, and to change the potential phi as being the fundamental solution of the Laplacian on that. So everything has a meaning, but from the physical point of view, at least I don't know. Yeah, but the question is valid. I mean, you can change the Laplacian by the Laplace-Beltrami operator, the potential B by the fundamental solution, and try to do the same thing. Yeah. No, the problem makes sense from the mathematical point of view, but we haven't done anything in that direction.
Can I ask a philosophical question out of sheer ignorance? You said that in the Thomas Fermi model, you don't have an excess charge problem.
Yeah.
So why introduce the von Weizsäcker correction?
No, yeah, there are many corrections to this model, right? I mean, the Thomas Fermi was the first density functional model introduced, right? And then people in chemistry, they started trying to make more realistic things. I mean, the Thomas Fermi is very easy to study because it's very simple and everything, but from the point of view of from the point of view of physics, it has dramatic problems, right? There are mainly two problems. One is the decay of rho at infinity, right? In the Thomas Fermi, of course, the decay of rho at infinity it goes like a power, and in real life, I mean, in chemistry, it goes exponentially, right? So that's a main difficulty, and the other main difficulty is that the solution to the Thomas Fermi equation at the origin is singular. And for the Schrödinger equation, they satisfy the Kato-Kasp condition, right? So they have a singularity, but the singularity is very mild. I mean, there is a cusp, right? And so the solution of the Thomas Fermi equation has really two big problems on the behavior. In the middle, in the region between 0 and infinity and the bulk, it's very nice. So that and so the other problem is that in the Thomas Fermi model, there are no molecules. You cannot. I mean, if you put, you consider one atom and another atom, and you put them together, they prefer to live apart. There are no. You can prove that there are no molecules, which is almost true. I mean, in nature, the atoms they are very much apart. I mean, when you have a molecule, the distance between the atoms in the molecule is huge. I mean, compared to the atomic scale. So in principle, Thomas and Fermi are not too bad. There are almost no molecules, but there are molecules, and they are very important in chemistry, right? So that's the other thing. But and so these are the three bad things: are the behavior of the rho near the origin, rho near infinity, and the fact that there are no negative values. But on the other hand, if you compute, as I said before, Barry Simon and Idle Deep in the 70s, they proved the connection between the Thomas Fermi and the solution to the Schrödinger equation for many particles. And you can compute the behavior of the energy as a function of the total charge C of the nucleus. And the leading power of that thing, I mean, so when you have a system that has charge C, and you study the behavior of the energy of the system as a function of C, the leading behavior is minus a constant times C to the 7/3, which is the right power from the Thomas Fermi. And then there are corrections, and there is a C-squared, the Scott correction, and but so in principle, from the point of view of energy, Thomas Fermi is great. But from the point of view of the behavior of the wave function near the origin and infinity, it's pretty bad. And also pretty bad. Well, it's not so bad in the sense that there are no molecules, because almost in life there are no molecules, and the atoms try to live. So and that's why I mean, at the very beginning in the 30s, von Weizsäcker introduced this correction to solve the problem of the behavior at infinity. And you see, when you introduce the gradient square, I mean, the solution immediately is going to decay exponentially, and also it's going to satisfy the gas conditions. So it's more or less evident that was needed. And then the Dirac also introduced a correction in the early 30s by I mean, when I said at the beginning that in the Thomas Fermi there are three energies: the kinetic energy, the expectation of the kinetic energy, the expectation of the attraction of the energy of the electron by the nuclei, and the repulsion energy. So the only exact term is the second one, and the other two are not. And Weizsäcker introduced the correction to the kinetic energy, and Dirac introduced the correction to the repulsion of the electron. And that's what I mean. He introduced the correct. I mean, what's called the indirect term. I mean, the D rho is the direct term, and the difference between the real expectation value and that it's called the indirect term. And from the physical point of view, so in physics it was introduced by Dirac, and it was studied mathematically by Lieb and Oxford in the 80s, and they tried to compute that quantity, the difference between these two terms in terms of rho, and that's called the Lieb-Oxford correction. So, but that's the reason why they needed to introduce them. And now in chemistry they have huge, I mean, they have enormous, horrible variational principles, right? There is a whole density functional theory.
Someone just got a Nobel Prize for it.
Huh? Yeah. There was a Nobel Prize in the 1980s. I don't remember exactly the year, but that was introduced in 1960. Yeah. Anyway, that's the reason why you have to introduce the von Weizsäcker.
Okay, thank you very much.